Okay, so for the gas laws, we are going to investigate the relationship between how gases behave when you change the pressure, when you change the volume, or when you change the temperature, or if you do all three at the same time. So again, these are laws, which means that they have been proven because it's very easy to manipulate these three particles or these three variables when you're talking about gas particles. So from the first note, STP is standard temperature and pressure. So sometimes the question will just say a sample of gas is at STP. They don't say what STP is. So you do need to reference the first note for this unit. So standard temperature is 0 degrees Celsius and standard pressure is 101.3 kPa. So these relationships are really going to be, very, very straightforward mathematical formulas where you know some of the variables and only one of them you don't. So you're going to do things like multiply and divide and stuff like that. So I sort of talked about this in the first lesson. If, at the very bare bones, if you have a negative divided by a positive or vice versa, or negative times a positive, your answer is going to be negative. So that's okay for temperature in degrees Celsius, but it's not okay for pressure and volume. That does not make any sense. So the way that we rectify that and make sure that the relationship follows what you would expect, then we're always going to convert degrees Celsius into Kelvin. So if we were having a gas test, you would get marks for that, and if you didn't do that, you would lose marks, okay? So always make sure you convert your degrees Celsius into Kelvin. If you do the homework and you want to check your answers, temperature has to be in Kelvin, or so your answer might look wrong, but all you've done is just forgotten to do that, okay? So Kelvin is degrees Celsius plus 273. It is not degrees Kelvin, it's just capital K, that is the unit, Kelvin. And remember, it's all based on absolute zero. You can't, absolute zero itself is still theoretical, but you definitely cannot go below absolute zero. So it doesn't have any negative values. So that helps with the math. So each of these laws are, on your note, are listed by the scientists or scientists who first sort of described them and investigated them or whatever. So even in a normal semester, I wouldn't expect you to, I wouldn't ask you what is Boyle's law, what is Charles' law. You just have to know the relationships between the pressure, volume, and temperature. So again, it's actually pretty straightforward, pretty common sense. So you don't need to memorize the person's name. So Boyle's law Boyle worked with pressure. So what happens when you change the pressure of a gas? So this picture is it's like a cylinder, which is really common. This occurs in the combustion engines we have in our cars, that the piston pushes down, creating less volume, increasing the pressure of gas, which is oxygen in a car, that kind of thing. So when you have, even if you can't read the numbers, that's fine. The particle space between them, they're trying to demonstrate whether it's like if you're close together, are you going to collide more often, that kind of thing. So big volume, the gas particles are kind of far away. Little volume, they start to get closer, and when you make it really small, then now they're even closer together. So when you have a small volume, then are you going to collide more often? Yes, you are. Sometimes I think about the classroom and pretend you guys are gas particles and think about like a little cubby underneath the computers. So if you are gas particles in this big classroom, is there a good chance you're going to collide with somebody else? No, you're not. You don't feel pressure from your gas particle classmates. If I tried to fit all of you underneath that computer or underneath a desk, would you feel pressure? Would you collide with your gas particle classmates? Yes. So pressure and volume exist in what we call an inverse relationship. Big volume, little pressure. Little volume, big pressure. When one goes up, the other one goes down, which is unique when we talk about the other relationships in this section. So Boyle's law is going to mathematically show what happens when you change the pressure and volume. So the first four, we're really looking at how does it change? What is the pressure, volume, or temperature at? And then what does the pressure, volume, or temperature become? So 1 and 2 is similar to the dilution formula, initial and final. So again, the math itself is pretty straightforward. You just have to make sure that you put the right pressure and volume together. So a sample of helium gas is collected in a 4.5 liter balloon at standard temperature and pressure. So we have its volume. The balloon is then submerged in a tub of water such that the external pressure is increased to 110.2 kPa. So when you're given STP, that's going to be a temperature and a pressure. But when you do the first three laws, the simple laws, then something is going to be constant. So here, this is saying temperature is constant, which means it doesn't change. So in our math, that means that we don't need to use it. It's sort of like it cancels out, okay? So it does say STP. We are not going to need the temperature because the temperature here is constant. So we need our balloon in 4.5 liters is at STP. Standard pressure is 101.3 kPa, so that happens to be our initial pressure. So it looks sort of like we don't have enough information in this question, and this is a common type of question in the homework, textbook homework, where it wants you to know what is STP, or the other one we talked about, SATP, so closer to room temperature. So you can just look those up in lesson 1, okay? So now we're going to submerge the balloon, and the external pressure is going to increase. So the final pressure, or pressure 2, is 110.2. And it says, what will the final volume be? So it's very straightforward. These questions usually are. It's telling you that we're looking for the final volume. You should check. We did yesterday look at converting pressure values. So this is kPa and this is kPa. So you want to make sure that your units match. So a question like this is really simple. It would be out of like 2. If I wanted you to convert pressure units, there would be more marks associated with it. For the most part in the homework, it's just straightforward like this, okay? So again, you're going to decide, do you want to rearrange the variables using the formula? Do you want to plug numbers in and then rearrange? Doesn't really matter. You don't need to keep units throughout your calculations. However, you must have units in your answer. And similar to what we've been doing before, if you have a good relationship with your calculator, you can do this all as one step. You can show a little bit more of your work. If you want. And we have KPA, KPA, so that means that they're going to cancel out. So we're left with liters. Is volume supposed to be liters? Yes. So now divide. Yes. No, only they just have to match. So if I for some reason wanted an extra mark, then I might say what is the volume in milliliters, but otherwise it doesn't matter. If you had a question where you were given volumes instead, so like liters and milliliters, you would have to make sure they match just like the pressure, but it doesn't matter. So you could do this with pressure in atmospheres or torrs or any of those as well. These are not meant to be tricky calculations. Okay, so the next one was discovered by a man named Charles. So he experimented with changing the temperature of a gas and how much space it filled up. So that picture is a hot air balloon. So when you heat the air up, then it starts to take up more space or expand, inflating the balloon, and you can, float all over the place and check out the scenery. So when you have volume and temperature, when you increase the temperature of gas particles, they start to move faster, which means they are going to take up more space. So temperature and volume are what we call a direct relationship. So the formula looks a little bit different. V1 and T1, V1 over T1 equals V2 over T2. So similar to any time when you have a fraction, like in grade 10 math when we do SOHCAHTOA and stuff like that, even the ratios that we've been doing before, you can have your variable that's unknown in the top of the fraction, in the bottom of the fraction. So there are different strategies for you to solve for that. You just kind of have to decide which one you like best. Okay? Actually, this is a good example right here. So in a glass syringe, a scientist draws exactly 25.5 centimeters cubed. Okay? So this is volume. You would have to remember that from grade 9 science. Grade 9 math. But it doesn't bother us. We can use centimeters cubed. And it sort of makes sense when you consider gases and how much space they're taking up, like cubic meters. It's a not a bad way to measure the volume. Of dry oxygen at 20 degrees Celsius from a metal cylinder. So our first temperature is 20. She needs to heat the oxygen for an experiment, so she places the syringe in an oven at 65 degrees Celsius. And leaves it there for 30 minutes. Assuming the atmospheric pressure stays the same, so there it is again, we're not concerned about pressure, it cancels out, it's the same. What volume will the oxygen occupy? So again, it tells us what we're looking for. So in this case, these temperatures are not negative. However, we are always just going to convert temperature into Kelvin. So again, all you're doing is adding 273. That's a pretty straightforward conversion. When you do this, you don't have to necessarily show your work. You could use the Kelvin numbers in the calculations, and I would accept that, okay? But here, I'll write it down so you can see. You want to write a little note for yourself? Okay, so this is not always necessarily going to have the unknown or the X in the top left. So maybe here you would prefer to cross multiply. It doesn't really matter. You can still do 25 divided by 293 and then multiply by 338, or you can cross multiply. Kelvin units cancel out. Our volume is going to be in centimeters cubed. No problem, okay? All right, so 293 times V2 is 25 times 338. I'm sort of running out of room. $8,450, and then you need to divide by 293 to isolate V2. And centimeters cubed. If you are a sentence kind of person, you can certainly use answer statements if that's where you choose to put your units instead of just stopping here. That's fine too. Just make sure your answer has the correct units. And if I want you to change it, then I would really, bold it or whatever. And it wouldn't be something weird like this, like cubic centimeters. It would be like milliliters to liters or something. Yes. I don't care. Okay. So the next one is a pair of scientists, Gay-Lussac's law, and dealt with um, pressure and temperature. So this is a pressure gauge. It kind of looks like a speedometer in your car, but it really can also be used to measure pressure. So this is a different type of question you could be asked. And again, depending on what kind of career you pursue, if you continue in science and have a science background, one of the things you might have to do is making sure that safety protocols are being followed or whatever, something like this, okay? So a cylinder of chlorine gas is stored in a concrete lined room for safety. The cylinder is designed to withstand 50 atmospheres of pressure. So ATM is atmospheres, that's fine, that was one of our pressure units. The pressure gauge reads 35 atmospheres, they match, excellent. At 23.2 degrees Celsius, an accidental fire in the room next door causes the temperature in the storage room to increase to 87.5 degrees Celsius. So we're going to find what the new pressure reads at this temperature, and then we're going to say, does the cylinder explode? So this kind of question, sometimes students are like, Ms. Todd, there's a lot of numbers here. I don't know what I'm supposed to use. So you have to really kind of read these questions carefully. So it says the cylinder is designed to withstand 50 atmospheres of pressure. And then it gives you a pressure with a temperature, changes the temperature, and asks you for a new pressure. So this 50 here, that's like the boundary or the limit. Okay? So will the cylinder explode? If it's less than 50, that's okay. That it's designed to withstand that. If it's over 50, then bad things will happen. So for part A, where we're trying to find the pressure when we increase the temperature, this 50, we don't need this at all, okay? So in a situation like this, you do really need to read the question carefully and make sure you're not using values when you don't need to, because technically there are two pressures and two temperatures. It almost looks like you don't need to do anything. So logically, if you increase temperature, particles are moving faster. Are they going to collide with more force? Yes. So pressure and temperature, like volume and temperature, they are direct. When one increases, the other increases. So it looks similar to Charles. P1 over T1 equals P2 over T2. So initially the pressure is 35. At 23.2, again, we want Kelvin. Pressure 2, 87.5. Oops. Sorry, temperature 2. which is 360 Kelvin. That's quite a big jump, but we're not going to guess. We want to be quantitative. So we're going to quantitatively figure out what our new pressure is, and then we're going to see, is it greater or less than 50, okay? So this one I showed a little bit different. You can do this all at once in your calculator. I encourage you, sometimes some calculators are tricky. I encourage you to do this times this. Either use brackets or push equals and then divide. Don't just do 35 times 360.5 divide by 296.2. The more instructions you give your calculator, the better it will go. So you get 42.6 atmospheres. Will the cylinder explode? Is it greater than the limit? No. So usually if this was a question, then you wouldn't just want to say no. Usually you have to state, give a support for your answer, a brief reason, whatever I say, okay? No, the pressure is less than 50. You could even be fancier. The new pressure is 46.2. That's less than 50, whatever. Yes. 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 Usually, I just wouldn't want you to write no, okay? So just make sure you would say why. But again, this kind of question would be like 1, 2, 3 marks plus 2 marks for this, a little bit more marks than if you don't have to do Kelvin, you don't have to do any sort of application to it, like the first example. Okay, so when we have gases are so easy to manipulate that often what happens is you can't just change the pressure without changing the volume and the temperature altogether. So let's say we'll continue with our example. So in this classroom right now, if your gas particles in this nice big volume, you are not colliding with somebody else, so your pressure is low, and you're probably not feeling very hot. If I tried to put you under there, and you were all squished together, you were colliding, your temperature would start to increase as well, right? So they often go together. So what you can do is combine them. So sometimes students will kind of freak out about this, but really it's all of the gas laws together, combined. So P1, V1 is Boyle's. When you look at Charles and Gay-Lussac's, all of them, both of them, because they're direct relationships, the temperature is in the bottom. Okay? So it takes into account the inverse relationship with pressure volume and the direct relationship with pressure temperature and volume temperature. So a situation like this one, where it talks about atmospheric conditions, this is much more a much more real world application. You're changing the pressure, temperature is going to change, and the amount of space it takes up is going to be different. So Billy the Chemistry Superstar is having a party to celebrate Mole Day. The day of the party, which is a thing, October 23rd, like 10 to the power of 23, it's a thing. The day of the party, the atmospheric conditions in the morning were -2 degrees Celsius. So the weird thing about negative numbers as well, then it can influence whether or not you can predict whether your answer should work, like if the pressure decreases, volume increases. So then, again, because we don't want negative volume or pressure, that helps with the math side, but also trying to interpret the gas laws as well. So this is definitely a case where we want to change it to Kelvin. And 100.8 kPa. A cold front moves in and the conditions change to 103 kPa. So the pressure is going to increase, and -25 degrees Celsius, which technically is temperature decreasing, even though the size of the number is getting bigger. See what I mean? Like, it's kind of messes you up. So if the pressure is increasing and temperature is decreasing, then that means the volume should decrease. So in order to mathematically get that the volume decreases, we need to change the temperature not into a negative number. Negatives kind of make our math nasty, okay? So the atmosphere conditions in the morning were -2, so temperature 1. And again, right away, I would just change that right into Kelvin. Okay, so -271 and 100.8 kPa. Often when you're talking about weather, people will use kPa. So if you listen to weather reports, they often use either kilopascals or just pascals. It doesn't have to be like that. You just want to make sure they match. So kPa, we're good, okay? So the volume of the balloons is 4.2 liters. And we're going to mathematically figure out what happens when you change the temperature. So now with Kelvin, a colder temperature is a smaller number, right? So that makes more sense mathematically. And it asks us what happens to the volume. So pressure increases, volume decreases. That means that temperature decreases. That means our volume should go down as well. Okay, so Kelvins cancel, kPAs cancel. So we're left with liters. And then again, you have to kind of decide how much work you want to show. So you can straight up just cross multiply right now. Some people, this is too much. So we can do 100.8 times 4.2, push equals, divide by 271. And then you can do this over here. 103 Is that right? 103? Yeah. 103 divided by 248. Okay, and then solve. If you round it a little bit different than me, then your answer might be slightly different. You could have cross multiplied as well. Most calculators, especially if you have a one with a display, will have an answer button. So then you can keep all the decimal places and round at the end if you like to do that. So we wanted to see our volume decrease. Did it decrease? Yes, it did. Okay. If we tried to use -2 and -25, meaning and -25, being a lower temperature, colder, it wouldn't have worked as nicely. It wouldn't have made sense. The last two gas laws are very, very straightforward. It almost seems too simple to be true, okay? So Dalton, and this is the same Dalton who had the 4 postulates from the atomic theory. He said that if you had a mixture of gases, then they each had their own pressure, and you could add them together to get the total pressure in the container. And that sort of seems like, yes, of course you could. Duh. So you would just keep adding the pressures, however many there were, in the container. So sometimes the questions are just straight up, add them together and find the total. This question's a little bit different. You know, again, this one's so easy that the teeniest little thing can maybe make it a tiny bit more tricky. So a mixture of nitrogen and carbon dioxide gas is at a pressure of 1 atmosphere and a temperature of 278 Kelvin. We don't even care about the temperature for this. If 30% of the mixture is nitrogen, what is the partial pressure of carbon dioxide? So it looks like we have a mixture of nitrogen and carbon dioxide. And it gives us the total. And weirdly, it says 30%. So you have to find 30% of 1. And again, sometimes it's just given to you here. The total's 1, so 30% of 1 is just 0.3. Okay, so as long as you don't use 30, which doesn't make any sense, how 30% of 1 is going to be 30? No, that doesn't work. So remember, with a percentage, you have to divide by 100. So this, for sure, you might even do in your head. So like I said, it's like they're, trying to make the easiest formula ever. Trying to find a way to make it weird, because it's almost impossible. Okay, so then you're just going to solve for PCO2, or the partial pressure of carbon dioxide. So you just have to subtract. And there's a variety of ways to do this. If 30% is nitrogen, that means that 70% has to be CO2. You could have done it that way. And then the last one is virtually identical, except now when you have like air, for example, or atmospheric pressure with the gas in the air, one of the gases that exerts a lot of pressure and always kind of has to be taken into account is water. So a common way to collect a gas is sort of to bubble it through water. So you can, and maybe you've seen this, you can really easily do this. You might have even done this in elementary school, depending on what your teacher was like, where you have a reaction that's producing gas, and then you have a tube that's got water in it. And so this would be closed. The only spot the gas can go is into the water underneath the tube, and then the gas goes in and the water comes out. But you have to take into account, you have to take into account what the water vapor pressure is, and that is actually a reference value. So in order to do this question, you have to be given that value, or when you go to do the homework, you look it up on table 1, in table 1 on page 596. So this is just Dalton's law of partial pressures applied to collecting gas over water. So this is like, this one here is the same as P total. And you'll always have water. What's the partial pressure of water? And then whatever gas you're collecting. That'll be it. So the partial pressure of water is dependent on temperature. So that makes sense. If you have a greater temperature, you're going to collect a greater percentage of water vapor. So in the question, the reason it's going to give you temperature is so that you can look at that up on that table. So hydrogen gas is collected using downward water displacement. If the atmospheric pressure is 150 kPa, 100.5, not 150, sorry. If you prefer total, you can write total every time, that's fine. And the temperature is 20 degrees Celsius. Determine the pressure of the hydrogen gas. Okay, so it tells you the temperature. So you have to go to table 1 on page 596 to find the water vapor at 20 degrees Celsius, which is 2.34. Okay? So not too much, but still enough. So kPa, we're good. And again, all we're doing is subtracting.